Good evening, Professor, classmates. This is Daniel Hudson coming to you from Diego Garcia. I am a part of the 3 Mile Island Accident Group, and I'm going to be talking about the plant design and associated discussion. So we're going to start out with the fact, that nuclear power plants, they have layers of defenses and redundancy to assure safety from radiological release. In the case of 3 Mile Island, there was 4 containment barriers designed to protect the public from radiation release. You have the reactor protection system, which is going to monitor critical parameters of the reactor system to automatically initiate a reactor shutdown. The engineered safety feature actuates a safety system when certain conditions are met to prevent damage to the fuel cladding. All these safety considerations are made to prevent a release of fission products to the atmosphere. So, rising control rods will raise reactor power, and that's how we generate heat. When the reactor is shut down and all fuel rods are inserted to the core, you're still going to produce decay heat. This decay heat is going to be around 7% of reactor power, so you're going to need to maintain some cooling during periods of shutdown. When you have, like what happened at 3 Mile Island when they turned off the reactor coolant pumps, that's when you can lead to fuel damage. You can start generating hydrogen, and if you go in excess of 5,000 degrees, you can have melting of the fuel material itself. So we'll start out by talking about the reactor coolant system itself, and we'll just kind of go through that as you would a drop of water. That's typically the best way to go about it. So 3 Mile Island 2 is a pressurized water reactor in which the reactor coolant is constructed from carbon steel and stainless steel. The high pressure and temperature water is circulated through the primary system by the reactor coolant pumps. These are large canned motor assembly pumps. So from there, we'll go through the steam generator, through the control rods in the reactor vessel, which is heated by the nuclear fission. The heat in the primary is transferred to the secondary system through the steam generators. With no forced circulation in the reactor coolant system, some plants are designed, 3 Mile Island was, for minimum use natural circulation, which means you have a difference in density that's caused by a difference in pressure due to a difference in temperature. Water is heated by the reactor in the hot leg, nominally around 600 degrees, and then it is circulated through the tubes in the steam generator. The steam generator removes this heat and gives its heat off to the secondary system, which goes to turn the turbines to create electrical power. So when it leaves the steam generator, it goes into what we call the cold leg with a nominal temperature of 545 degrees. Also the pressurizer, which is connected to the hot leg, and it maintains pressure in the reactor vessel above the boiling pressure at nominally 2,200 pounds with installed heaters. That'll keep above a saturation temperature of greater than 650 degrees. Also, things that we monitor is there's pressurizer levels that are monitored, and it also acts as a surge volume for any changes in plant temperature. The reactor is protected by power operated relief valves, PORVs. You've also got pressurizer spray, and as we previously discussed, the reactor protection system. The PORVs are equipped with isolation valves known as block valves to isolate the PORVs if they stick open. As Steve will talk about here in a little bit, that played a central role in 3 Mile Island. The relief valves and the safety valve discharge in the reactor coolant drain tank, which is equipped with thermocouples to detect any downstream leakage. The reactor coolant drain tank has a relief valve set point of 150 pounds and a ruptured diaphragm that is designed to burst at 195. The drain tank relief valve and diaphragm discharge valve discharge directly into the reactor building. So we talked about the primary, some of the primary systems and safety systems. Now we'll talk briefly about the steam generating system. The feed and condensate system will take suction from the condenser and pumps water to the steam generators. This is just a Carnot steam engine. The steam generator water level is maintained in band in the event of a loss of the feed water supply. Emergency feed water from 3 pumps will supply auxiliary fluid through the auxiliary feed nozzle. The auxiliary feed water is needed immediately following the loss of a feed water event in order to remove residual heat from the reactor core. The steam generator delivers steam to the high pressure turbines and allows the main generator to provide power to the electrical grid. Besides other steam auxiliaries, the steam is also delivered to the steam-powered main and emergency steam feed water pump turbines. This is going to control steam generator pressure when the turbine is not online. The steam generator also has safety valves. It also has atmospheric dump valves and turbine bypass valves for safety and control. The steam generator safety and atmospheric dump valves discharge outside of the turbine building directly to the environment. This is, again, a benefit of having a pressurized water reactor, as you have a clean secondary side, so you are able to do things like that. The condenser has, with the cooling water circulating through it, operates at a vacuum and condenses steam that exits the turbine. As we know, a Carnot steam engine, you have to have that phase change take place of the exhausted steam back into the water so it can get pumped back to the steam generator. The circulating water pump takes its suction from the basin. It circulates water through the condenser and is sprayed back into the cooling tower. As the water falls into the basin, the water is cooled by the air, making it way up to the cooling tower. The turbine bypass valve discharges steam directly into the main condensers. On a loss of condenser vacuum, there's an interlock which will prevent the turbine bypass valves from opening and will automatically switch pressure control to the atmospheric dump valves. In order to maintain the vacuum, there's also lower pressure auxiliary steam. So there's the main steam header. There's reducers that will provide lower power steam, which is provided by an auxiliary boiler. And so when you start up the main steam system, you can draw a vacuum. The last thing we're going to talk about is some emergency auxiliaries. There was an emergency core cooling system, and it is designed to cool the reactor core following design basis events for a loss of coolant casualty, or a control rod ejection, main steam, or a feed header rupture, or a steam generator ruptured tube. There's 3 basic systems or components that make up the emergency core cooling system. You have the high pressure injection system, the low pressure injection system, and the core flood system. 3 parallel makeup pumps take letdown flow, purify it, and supply it back to the reactor coolant system. The makeup flow control valves senses a decrease in the pressurizer level and repositions the control level. The high pressure injection system uses makeup pumps to inject high pressure water into the reactor coolant system during a loss of coolant casualty. In the event of a small reactor leak with the reactor pressure is lowering, the high pressure injection will take its suctions from 2 sources. There's a letdown cooler and the borated water storage tank, and as we know, borated water is a poison. The borated water storage tanks held 300,000 gallons of borated water. It'll add the boron to the primary, and it can be connected to the spray system to lower reactor building pressure. The low pressure injection is known as the decay heat removal system, and that's going to provide a long-term decay heat removal by pumping directly to the reactor vessel when pressure is less than 180 pounds. The Core flood system is going to provide cooling following a large pipe break. This is the safety feature of last resort. The core flood tank contains borated water and is pressurized by nitrogen at 600 pounds. Stop valves are in place to isolate the tank during shutdown to prevent injections. This system is independent of actuation signals, electrical power supplies, or operator action. Each core tank holds 7,800 gallons of borated water. When the reactor pressure drops below 600 pounds, the check valves open and water is injected into the vessel until the check valves reclose. I would like to also prepare for my next partner, Steve McKee, who's going to go into more detail about the accident itself. Thank you for your time. Have a good day.